Okay, yeah. So welcome back, everyone, to our GLab seminar. So today we're very happy to have Alejandro Cabrera speaking about differentiation of high-Lie groupoids and generalized finesse theory. So as you know, this is an informal seminar, so we should have plenty of time. So if you have questions at any point, please feel free to unmute yourself and ask your questions. Okay, so Alejandro, the floor is yours.
Yes. Okay. Thanks a lot, Martin, for the invitation. It's my pleasure to be in this seminar. I think I saw it even before it existed, and then it was formalized, I guess. Geometric structures. It became a lab. And okay, so I'm going to speak about this project that is together with Matías Deloyo, and that I already spoke about this project on a meeting that we had last year in Manaus, in Brazil. So some of you, like Eckhart, already saw part of the slides. I slightly updated the slides, but my idea is to give a general introduction to the topic, to what we did, and then counting on the fact that there will be questions or extended sessions for questions at the end. So if you already saw it, I apologize if you remember very well what I said, but okay. Great. So this is the outline. First, I will do a more general introduction. Then I will speak about let's say, one of the main results, which is a differentiation process for higher groupoids. And finally, I will speak about the generalization of Van Nest isomorphism theorem. And as I said, I'm counting on discussion afterwards. Okay, so as Martin said, please ask me at any point. So here is the first part, which is an introduction. There is this Zoom things that block my view, but okay, you probably can see this perfectly. So I will do a very short review of classical Lie theory for groups and groupoids, trying to highlight some things that we will keep in the more general case. I like to think in this way: if we have a Lie group of, let's say, transformations, for example, orthogonal transformations, you can think of a family like this that deforms the identity matrix, let's say. And the first order deformation parameter, it will be a skew symmetric matrix in that case. And that's what the Lie algebra is formed of these infinitesimal parameters of transformations. Of course, when you look at the product, then you obtain the Lie bracket on this Lie algebra. And for groupoids, this particular aspect is very analogous. You only need to keep track of the fact that there are many identities, but you can think of an identity arrow like here that is deforming over time into a non-identity arrow, and the first order parameter will be an element on the Lie algebra. So it's very parallel. Okay. Another piece that I want to recall is the Van Nest map that can be defined at the level of cochains. So let me first review what are cochains for a group, for example. So they are just smooth functions, which I take to be normalized. I will come back to this a bit later. It means that whenever one of the inputs of these k power inputs is an identity, then the function vanishes. Then there is a simplicial differential, so this becomes a cochain complex, and there is also a cup product. that will play an important role is non-commutative. And on the infinitesimal side, as we all know, there is this exterior algebra of cochains with Chevalier-Eilenberg differential that codifies the Lie bracket, and there is the wedge product, which now is graded commutative. So going from left to right takes this non-commutative product into the commutative product, which is a sort of abelianization that also plays an important role in the general case. And I will call this Van Es map V. So it's both, so it preserves the differential and the product. Okay. So a classical theorem of Van Est is that when the group is n-connected, then the Van Est map induces isomorphism in cohomologies for, I forgot to write it here. Let's see if I can add it quickly. It's for all degrees. Oops. Oh, something is not right. Okay, it's for all degrees k less or equal than n. What do I want to say about this? Oh, okay, I think I'm saying about integrating cocycles because this is a natural question, I think, in classical Lie theory. For example, if you have a projective representation of the Lie algebra, then there is a two cocycle associated to the fact that it's projective, and it's a natural question whether this cocycle comes from the group. And well, if it is two connected, then yes. And in this way, you can promote representations of the Lie algebra to the group and so on. So this is a very classical matter, as far as I understand. And there is a generalization to Lie groupoids and algebroids due to Marius Kreinig, and also there is further work, characterization of David Leblanc and Eckhart. So, okay, this is what I would consider this classical part. So here we have a title that I don't see. Higher. Okay, so I want, this talk is about higher Lie theory. So there are many motivations to consider, as you probably many of you know in the audience. For example, homotopy Lie algebras, representations up to homotopy. Well, in the world of extended field theories, then there is a more modern language like shifted geometry, and more specialized generalized geometry, that the number two of the shift appears, current algebraics and so on. So there are many reasons why one is led to higher versions. And so in this world, there are many challenges. Even in the most basic aspects of the theory, as I was saying, for example, groups and groupoids, although one has to be careful and so on, many of the basic aspects are very parallel. But this doesn't hold for higher. For example, there is no like multiplication operation in general. It's only a relation. So you cannot really define right invariant or left invariant objects. So one needs a purely simplicial description. Another point is that there are coherence identities, as you know, for example, on a higher Lie algebra, that can be very complicated. So you have to have a very good reason why this hold. Checking them by hand, one by one, is not a good idea in general. And another aspect is that if one thinks in this very simplified way that I presented a family of transformations, and you kept the first order like here. Now you are led naturally to think of multi-parameter families. You can think of these different times, T1, T2, and so on, as being coordinates on a geometric simplex. And the point that I want to make here is that these higher order Taylor coefficients play a fundamental role, just as in the usual theory, the first order ones played a fundamental role, defining the Lie algebra and so on. Okay, so these are the challenges, and now I want to review very in an ad hoc way the literature. This is not exhaustive at all. I just wanted to mention some references that anyone or that people that ever thought about this encountered, and where the things that I'm going to say later stand with respect to the literature. So first of all, there are many references to the work of Sullivan within rational homotopy theory. I think, as far as I know, it was the first time that the idea of taking certain DGAs that are minimal and so on, and doing a simplicial procedure to produce a space that plays the role, analogous role to a Lie group integrating a Lie algebra, but with more generality appeared. There is even a theorem within that paper, 8.1 prime or something, that he says that is an analog of Van Ness theorem. So there are many very general ideas here that touch the simplicial aspects. Then there is lots of very fundamental work of Getzler, then André Enriquez, and many others that I'm not mentioning for algebra. So over a point, let's say, L infinity algebras. Then the question of how to differentiate a higher Lie groupoid into a higher Lie algebroid was touched upon in many instances. Some of them are general, like this very interesting paper of Cabrera, and then it was expanded with technical aspects by these authors. And then in particular cases, for example, by these other authors. So that's the differentiation process. And about the integration process, which is more complicated, there is this very general work of Cabrera and Tiran that produces a local version, just as you can have a local group instead of a group. So this one, again, Leblanc, Cabrera, they have a also interesting paper about the particular case of exact current algebroids. Then for bi-algebroids, there is the work of Mehta and Tang. Then for a certain order 2 object associated to a quadratic Lie algebra, there is this paper of Kwek and Xu. So from this point of view, it looks like many things were done. So why are we coming back to the differentiation process? And the general procedure described here, of course, is conceptually very insightful, but it has some technical problems when you try to make it concrete. And in particular, this process produces a super manifold, or if you want a DGA, but it's defined very indirectly as a certain functor, and then you have to prove that it's representable. But in this process, although the abstract functor carries a natural, in particular, differential that contains the infinitesimal information, Lie brackets, higher brackets, and so on. When you make concrete the supermanifold, you represent it, then it's very hard to keep track of it, because you need to put additional information. So there is like a short blanket kind of problem there. It's hard to make concrete. And in a way, one could say also that there should be a much more elementary procedure to take a higher groupoid and produce a higher algebroid just with elementary notions and so on. And this is what we achieved. And once that is clear, we, for example, proved the third theorem that I will speak about today of the isomorphism and everything. Because once it's put into this more, I would say, solid and handable grounds, it's better, it's easier even to prove general facts. Another comment that I want to say that I will mention again is that when one, in this procedure of Pavel-Cabrera, by definition, supermanifold is defined, and by definition, this entails graded commutativity. Supermanifold is defined by, let's say, a graded commutative algebra of function. So graded commutativity is put by hand there. And in our work, we discovered that this is actually a consequence of certain simplicial coherence. So in this process, I think I would like to convince you that we also unearthed some more basic facts about this differentiation. Okay. So now I want to, so in this talk, the aim is to define this differentiation procedure and some elements of Lie theory having focus on cochains. So now this will be an outline of the talk. First of all, the most important point is we identify a certain ideal or inside cochains that has the information of what differentiation does. Then the first two theorems tells us that when we divide by this ideal, then we get exactly cochains for higher algebra. So it does two things at the same time. It defines the cochains, but also it defines the algebra. So it defines the differentiation procedure. In particular, we get a generalization of the Vanness map. Takes a cochain on G and it gives a cochain on the algebra. But the way we do this, for example, the fact that it's a chain map and so on, it's all automatic. So the non-trivial part of this theorem is to prove a regularity. You could take any ideal and divide, and in general, it won't be commutative, it won't be freely generated, and so on. So this regularity theorem 2. And also, I should say that I was saying the ideal has built into it the conceptual aspect. What is differentiation doing? Okay. So here are some remarks. As I was saying, graded commutativity, it's an emergent thing from our point of view. It also factors through the local version. So this is similar to standard Lie theory. If you have a group and you restrict to a local group, a neighborhood of the identity, it has the same Lie algebra. It also works for infinity groupoids. And one may wonder what happens if instead of cochains, which are functions, I take forms. Okay, it works exactly the same. So very minor. It's almost a corollary that you also get a Veil algebra and so on, and a Vanness map at the level of forms. Good. And the third theorem is this, it's a generalization of the Van Ness isomorphism theorem that I mentioned in the beginning, that when a certain connectedness assumption is met, that I will make precise later, then differentiation, it's an isomorphism in cohomology in all these degrees. So this is a generalization of that theorem. Okay, any question at this point? Great.
Well, maybe you're going to
Yes.
say this, but is it easy to say what the ideal is in the case of a group?
Of a group?
Yeah.
Yeah, we will do this in a second.
Okay, thanks.
Yeah, this was more of a spoiler.
Sure.
Just to tell you where we are going. But yes, we will
Okay.
speak about this idea. Okay, so
Thanks.
now I will introduce basic definitions in order to then provide the relevant definitions. So the idea is to consider a simplicial manifold. So for each n, I have a manifold Gn, and for each simplicial elementary map like this, for the ordinals n and k and so on, I have a smooth map between gk and gn. In particular, the elementary phase and degeneracy maps get promoted to smooth maps, which we call phase maps and degeneracy. So here I depicted more or less what I'm writing. For zero simplices are just points in this manifold G0. So one simplices are points in this manifold G1, which we think of representing the abstract one simplex like this, 0, 1. And degeneration, we can think of a limit in which these 2 points, 0 and 1, coincide. So we just go back to having only 1 point. Similarly, with two simplex, with this triangle, here D0 is the opposite face to the 0 vertex and so on. And there are two degenerations when 0 and 1 vertex coincide, which is this here, and 1 and 2 when these two other coincide. So these are the two degenerations. The generations, as we will see, and it will play a major role, they define submanifolds inside G2. So G2, we think of geometrically, it's a manifold that has two distinguished submanifolds, and they intersect in G0, in a sense, seen inside there, which is a completely degenerate triangle. So to say what a higher groupoid is, I have to speak about filling horn condition. So the horn, for example, the horn of this triangle based at 0 vertex is this. You remove the interior, so the dimension 2 part, and I also remove the opposite face, which in this case is this edge. So I just get two edges united at this 0. So there are two conditions. One, well, this is technical, that the space of horns is actually a smooth submanifold inside the product. And the other one is that the map that forgets about the filling and so on and gives you the horn is surjective submersion. So surjective means that whenever I have a horn, I can fill it. The filling might not be unique, but you can fill it. And submersion, of course, is regularity, that any infinitesimal deformation of the horn can be matched by the infinitesimal deformation of the filling. Okay, so this would be an abstract higher groupoid, and we say that it's an n groupoid, big N, that it's a number, when the filling is unique after a certain dimension. Okay, the dimension big N. For example, if the filling is unique after 0 dimension, then we have essentially a manifold. For n equals 1, we recover Lie groupoids. And for n equals 2, we get new stuff. For example, VB groupoids, for those who know, arise this way, gerbs, and so on. So just to make it clear again, n equals 2 means that, for example, when you have a tetrahedron, a 3-dimensional thing, and you consider the horn, the filling is unique in dimension 3. So it's non-unique up to 2, and then it becomes unique after 2. So now I will define very briefly cochains. Again, these are smooth functions on these spaces of simplices that are normalized. And normalized means that whenever I restrict to one of the degeneracy submanifolds, the function vanishes. So normalized cochains, they form a complex with this differential. If we had taken not normalized cochains, they are quasi-isomorphic, so that's not a big thing. So the differential is this one, is the alternate sum of the faces. And there is a cup product. It's defined by when you take two functions on Gn and Gm, you can think that f is evaluated on the last n faces, and f2 is evaluated on the first m faces, and then you just pull them back by the phase map and multiply them pointwise. So this is the cup product, and as I said, it's non-commutative because what happens in the first phases has nothing to do with what happens in the last phase. So if I do it opposite, I just get something different. Okay, so that's the cup product, and the differential, it's a derivation of the product. When we have groupoids, we get the familiar differentiable cohomology. If we take forms instead of functions, everything is analogous, and we get another. Now it's a double complex because we also have the RAM differential. It's called in many references Bott-Schumann complex, and it's related to the cohomology of some classifying space and so on. But as I said, to the effect of differentiation, once you understand cochains like functions, the going to forms is immediate. There is nothing more complicated there. So I'll just stick to forms because of that. Okay, good. So now I begin with something relatively new. So I'm going to define something called a frame. So a frame will be, so it will be a normal form for these spaces of simplices around the completely degenerate simplex, which was G0. So around G0, we will have a normal form. And that will be our first theorem. So first I introduce linearized data. So I mentioned the fact that filling a horn is not unique. So these vector bundles EK, they are vector bundles over G0. They parameterize infinitesimally how many ways I have to, for example, fill a triangle, like in this animation here. So even if the boundary is fixed, we can fill it in different forms. And this will be parameterized by this vector bundle E2. Here, well, filling a horn is essentially, in dimension 1, it's just fixing the 0 vertex, and then I just extend it to any arrow. So the E1, in the case of a Lie groupoid, for those who know, of course, E1 will be the vector space of the Lie algebra itself. Okay, so we have these vector bundles Ek, and as I was saying, they parameterize the non-uniqueness. So if, for example, if we have a big N groupoid, higher groupoid, then this vector bundle is trivial, is zero rank for K bigger than N. So now in this, but of course, this is linearized. So just take the differential of the map and look at the kernel. And at the linearized level, there is lots of work in the context of Dold-Kahn correspondence. In particular, think of this way. Suppose that you have ambiguity in producing an edge. And you also...
Sorry, Ali, may I interrupt? In the first line, is the K in N by any chance, or?
Oh, sorry, yeah.
Okay.
Yeah, K is N, sorry. Yes, thank you. Right, so I want to explain now this direct sum that might look a bit weird. It addresses a certain combinatoric kind of problem, which is that, for example, if you have ambiguity to produce an edge, which is the E1, you have ambiguity to fill a triangle, this is the E2, and so on. You can imagine that when you want to fill up a tetrahedron, a three-dimensional one, all these ambiguities pile up, right? Because you can, each edge will be ambiguous, each face will be ambiguous, and then there is the new ambiguity of the three-dimensional thing. So this formula captures that at the linear level. So you can parameterize these different ambiguities by this surjective order preserving maps. Okay, so this alpha is an order preserving map from and this, as I was saying, this is of course absolutely not new. This is known from in the Dold-Kahn correspondence. But in particular, so the normal bundle, so if I have a completely degenerate N simplex, I can deform it in many directions. These directions are parameterized by these maps alpha. If I choose one such alpha, then I get a normal coordinate, or a normal direction of parameters. I will call them Z alpha. Another thing that is known from this Dold-Kahn, the linear Dold-Kahn case, is that in this decomposition, the phase and the degeneracy maps take a normal form, which can be expressed like this. It can be expressed in other ways. This sum is over alphas, so beta is fixed, and you have to factorize beta like this with the elementary injection delta and so on. So these sums are either trivial, so you get 0, or it has one term only, or 2 terms, and that's it. You don't get more than 2 terms. In the D and in the S, you get either 0 or 1 term. So it's written in a more complicated way, but that's what you get. So it's a very concrete normal form. And I put except I0 because when we look at this normal bundle and so on, we are taking the horn based on 0. So the D0 map is external to all this. Okay. So this slide, the takeout is that on Gn, we have this submanifold G0 that is completely degenerate simplices, and we have control on the normal bundle. This is based on simplicial considerations, linearized simplicial consideration. So the frame will be a statement that in a tubular neighborhood sense, we can take any higher groupoid into this normal form.
Is this decomposition canonical?
Sorry?
The direct sum decomposition, is it canonical?
Yeah, this is canonical in the sense, I mean, there are conventions, different conventions that you could choose. You could, instead of surjective maps, you could take injective maps and so on. But yeah, there is no arbitrary choice here.
Okay.
Up to the convention. Does that make sense?
Yes, thanks.
It's a bit like, for example, when you have a groupoid, you could take kernel of the source or kernel of the target, but both, once you choose one, there is nothing. Yeah, it's a bit like that. Okay, so a frame, as I was saying, for each n, you get a neighborhood of the zero section in this normal bundle. That is an open embedding into Gn that takes the structure maps S and D into the normal form that I mentioned. And again, it's all of them, but not the zero map. If you could do it for the zero map, it will be a super special case. We can think of this already for groupoids, and in little n equals 1. So you have the space of the groupoid. Maybe I'll try to draw this. Okay. Now I turn the pen. Okay. So I will do, sorry, it's very hard to draw. So this is G1 for a groupoid. So it's the total space of some curly G groupoid. And we know that there is a distinguished submanifold here that is the identities. And there are two maps. If I have a point here, there are two maps, the source and the target. That with this notation, it would be the target is D0 and the source is D1. So of course, I can always find a tubular neighborhood that rectifies D1 in the sense that D1 now coincides with the bundle projection. I just take a kernel of the differential of D1 and do a usual tubular neighborhood. But then D0 will be whatever it has to be, right? So it will be very, very particular case to be able to rectify both D0 and D1 at the same time. It will never happen. I mean, in general, it will never happen. So something similar happens here. We have to leave D0 out because of this reason, and D0 will contain all the information in this frame, all the relevant information in this frame. Okay, so the first theorem is that every higher groupoid admits a frame. So let me say briefly how to prove it. We do it inductively, and as I was saying, in the first step, we just take an arbitrary tubular neighborhood adapted to the map D1. Then when you go up, you have to work a bit, and it's similar to certain things that are done in Dolkan at the linear level. So Dolkan is in the context of vector space or vector bundles, if you want, but everything is linear, so you have to take kernels and things like that. You can adapt those things to nonlinear case, which, as we have here, for example, thinking of something called microbundle. But then once you build this phi n inductively like this, it might not be compatible with the degeneracy maps. So you do it so that it's compatible with the phase maps, but the degeneracy is, you have to do use a certain gauge freedom. And so you have to work a bit more, but in the end, it just works, and you can always take it to this normal form. So in the normal form, you have this, let me go back. the normal form, you see this, the composition, and all the structure maps have a very concrete form, except for D0 that can be nonlinear. For example, in this drawing that I did, it would be the anchor map. I mean, nonlinear in a certain sense, right? It will have information, relevant information that has not been normalized, the anchor of the groupoid. Okay. And again, if I take D0, but now one level up, in the case of a groupoid, D0 will contain the information of the Lie bracket on the algebra. Okay. And in that case, there won't be any further information, but in higher groupoids, D0 will contain the information of all the higher brackets of the higher Lie algebra. They will all be in D0. Okay. So this is the first theorem. So now we move more into the more specific thing that I was saying, this ideal J. So the ideal J is defined by a set of generators. So it will be the ideal generated by this J0. And this is essentially the most key point of the talk, that one considers functions that have excess of vanishing at the degeneracy locus. So in Gn, you have these submanifolds given by degeneracies that they all intersect in G0. And because the function is normalized, so it vanishes on all these submanifolds. So the order of vanishing is already n, okay, which is the number of submanifolds. But we consider functions that have one more order of vanishing, okay? In algebraic terms, it will be this formula. So we take ij, the vanishing ideal of the submanifold Sj, and having higher vanishing means that it's in the ideal square. So if the submanifold is given by an equation x equals 0, now these functions, they behave like x squared. And then we sum over the J, which indexes the degeneracy submanifold. Okay. Good. So this higher order of vanishing, it's related to these Taylor coefficients that I mentioned before. The idea is that because we will declare this to be an ideal that we will mod out, this higher vanishing is uninteresting. So we only keep the information that doesn't have higher vanishing. Okay. Great. So these are the generators, higher vanishing. Here there are some simple animations. When you have an arbitrary curve going into, here is G1 going into S0, you can think of a groupoid and the identities, and you evaluate your function f on this curve, then it will have vanishing t squared instead of just t. That's the higher. Here, for example, I'm approaching one of the degenerations where these 2 points coincide. And again, I will need t squared vanishing along any such curve. And here is to mention that you can approach in another direction by considering different fillings, and you still will need t squared. But the interesting thing, although in the drawing it doesn't show, the boundary of the triangle could already be completely degenerate, and the filling will be something like a bubble, a sphere. So what will happen is that the coordinates corresponding to different fillings will naturally be of order 2, because they vanish on both the S0 and S1. Okay. Good.
I think I remarked this already in Manaus. This kind of setting is basically like an example of what we have for weightings.
Yeah,
If one has a
yes.
collection of submanifolds which intersect cleanly, cleaning meaning that in local coordinates they look like coordinate subspaces,
Mm-hmm.
then along that intersection one gets a weighting of that
Yes,
intersection, and this order of vanishing is exactly the filtration corresponding to that weighting.
exactly. Yes, yes. We should. I have it in my to-do list to make the connection more precise. But yeah, the weight that Eckhart is mentioning is exactly the order. So I'm saying that the coordinate that controls the different feelings is of weight 2, because it vanishes at order 1 on both. Total weight 2. So yeah, exactly. The order of vanishing is the weight. Thank you. So, okay. So this is J0 is generators, and then you can consider the ideal generated by it under both operations, delta and the cap product. And this defines, by definition, a differential graded ideal, which is the main object. One comment is that when you unwind the definitions, this J0 is already an ideal for the cap product. So the only new thing that you need to add is this piece. So delta of J0. Maybe I'll erase. So the J is essentially this higher order vanishing and delta of functions of lower degree that come from Gn minus 1. So one immediate lemma that is very interesting here is that when you quotient by this J0, it's an algebra that localizes around G0, so around completely degenerate simplices. What does this mean? That if I have two functions which coincide, whose germ coincide around G0, then in the quotient they will be the same element. It doesn't matter what happens far away from G0. So this is already interesting. And then we further have to divide by this extra piece. But already we know that when we divide by J, we get localization around G0. And in particular, we can use a frame to describe what happens. Okay. So one example that I'm going to work out briefly. Later we can do more details. But so suppose that we have the nerve of a Lie group, curly G. It could be a groupoid as well, but for a group it's easier. So what happens? I want to describe what I get in the quotient in dimension 1, C1 modulo G1. In this dimension, if you unwind the definitions, you only divide by the generators of higher vanishing. And again, as I was saying, when you unwind the definition in this particular case, you only have one submanifold, which now is a point, is the identity. So we have functions that vanish on the identity and vanish, the ones that have higher vanishing, they behave like x squared. If x is a variable, let's say in exponential coordinates, for example, that measures the distance to the identity that on the Lie algebra is just 0. Okay, so when I take a function, on 0 it will be 0 because of normalization. The function is normalized. Then it will have a linear term in the Taylor expansion, and then we will have quadratic terms. But these are all in J0. Let's see if I can write it. These are in J0. precisely because they have a quadratic vanishing instead of just linear. So the only information that we get after the quotient is just this linear part. So it's an element of the dual. It's a linear function. Great. So this is an easy computation. So we see that when we do this quotient, we recover the dual of the Lie algebra. Now, what happens for two simplices? Here, this J is not just the generators. You also have, so J2 is this, that it implies order 3 of vanishing. But we also have delta of J01. So I will do it in 2 steps. First, I will see what happens with the quotient by this, and then I will see what happens with the quotient by this. So if I divide by this J0, I claim that I get G star tensor G star. How does it work? It works like this. Again, I take an arbitrary function here. So F belongs to here. So it's group times group. And normalization means that F 0x has to be equal. So whenever one of the two entries is an identity, which in these coordinates is 0, it has to vanish. Okay. So when I do a Taylor expansion, all the first terms that I wrote here, even the quadratic terms where you take where you take the derivative with respect to the same factor, they all vanish because of normalization. So the first non-trivial term is this one, is the mixed derivatives term with respect to x1 and with respect to x2. So it's a bilinear form, and that gives you this term. And then I get cubic terms in the Taylor expansion that they are all, we don't care because they are in this cubic vanishing, which is A02. Correct? So this is what justifies this claim, is very simple Taylor expansion. Now, the direction we are going is the following, that if I divide not by just J0, but by the full ideal J, I should get wedge 2, so the Chevalier-Eilenberg in degree 2. And yes, this can be checked. I won't do it now. I can tell you a bit later how it works. But the idea is that this new factor has more relations on the quotient. And from this part, I can divide this tensor product into the symmetric, plus and skew symmetric. So the new identities that come from here kill the symmetric part, and you just get the skew symmetric part of the bilinear form. So that's how it works. As I was saying, in this particular case, you just take the definitions, work things out with just simple Taylor expansions, and you find the exterior algebra directly. With just a bit more, for example, having in mind the Baker-Campbell-Hausdorff formula, you can also deduce very elementary way that the delta in the quotient goes to the Chevalier-Eilenberg, and that the cup product goes to the wedge product. So in this particular case, it's an exercise to verify that the claim that I was making, that when you divide by J, you get the Chevalier-Eilenberg of the Lie algebra. More generally, is way more complicated because of these different weights that appear and so on, but that will be the theorem. For example, now suppose that we have a general higher groupoid, and I want to tell you what happens in degree 2. So what happens in degree 2 is that when I first mod out by this J0 part of the ideal, I get essentially polynomials in these variables with coefficients in functions on G0. And as Eckhart was mentioning, these coordinates have weights. So these two coordinates have weight 1, and this one has weight 2. And that's why they appear multiplied together. So we will have polynomials which are quadratic on these two, just to get order 2 of vanishing. Again, here is the illustration that these coordinates represent, as Eckhart was saying, vanishing of like normal coordinates to this submanifold. So if I take a normal coordinate to this submanifold, this would be this one. For example, if I take a normal coordinate to the other one, it will be the other one. But then there is a third dimension in this drawing that represents this one, that vanishes on both. Okay. Good. So dividing further by the full J ideal, we get this. The wedge 2 of the coordinates of order 1, and we get the pure degree 2 coordinates. So, and again, this could be, it's a bit more complicated, but you can do it just by hand, by taking Taylor expansions and thinking a bit and looking that this kills the symmetric part of the quadratic Taylor expansion and so on, and that's it. When you try to do this coherently for all degrees n, you need a bit more technology, and this is what the second theorem is. So first of all, I want to recall what a higher Lie algebroid is very quickly, because I'm going over time. But so a higher Lie algebroid, you can define it in this way. There are different definitions. One is this one, that it's given by a DGA such that in non-negative degrees, the degree 0 is functions on some manifold that you can think of the body, and that non-canonically it's graded symmetric algebra defined by a graded vector bundle. Morphisms are morphisms of DGA going in the other direction and so on. So in the case of a Lie algebra, the idea is define the Lie algebra structure through the Chevalier-Eilenberg complex. That's what's going on. The same for algebroids. If you want a more geometric version, here are some cases, but if you use the language of supermanifolds, you can think that this algebra is actually functions on a supermanifold, and the differential is just a vector field that happens to square to 0.
So if you have a double Lie algebroid and you have the corresponding Weyl algebra, you take the kind of total complex. Would that be an example?
I think so. Yes, but it's a bit. Yeah, I think so. Yes.
Or maybe a related question: if you take the higher tangent bundle T, like these jets of paths,
Yes.
would those be examples?
Well, in the case of jets, I don't know what the differential would be, but in the case of T, there is an obvious the RAM differential, but in the case of jets, I don't know. Maybe you know it, but it might have to do with these worms or gorms that Pavel has. Yeah. But we
Okay.
can think of it more later.
Mhm.
Yeah, in the double case, you will have by grading and you could take the total grading and so on. I think this should work. Okay, so this is the second theorem, as I was saying, that in the way this thing is being defined is like this, that when you take the quotient is very regular. It's cochains on a certain higher Lie algebroid. This is uniquely defined in this way, the Lie algebroid structure. And moreover, whenever you have a frame for G, it induces one of these infinitesimal frames for the algebra. So you can split the coordinates into the ones that are pure degree 1, pure degree 2, and so on. And of course, the vector space, the vector bundles that appear here, E1, E2, are the ones that we already saw, the ones that control the infinitesimal filling. So that's the second theorem. So it does two things at once. First of all, it characterizes the quotient, but it also defines the algebra. I think that this procedure to define the algebroid and cochains and so on has many advantages. One of them, I mean, it makes many of the properties of this differentiation extremely clear. For example, if you think of how this J was defined, it was purely simplicial. So whenever you have a simplicial map, everything will go through. So this is functorial. Other consequence is that it comes for free with a Van Est map because it's the quotient map. So when you have a cochain in G, you just take its class, and that's the cochain in the algebra that is the infinitesimal version. Another comment is that this local thing, as I was saying, when you have a group, you can take a neighborhood of the identity is a local group, and the Lie algebra of that is the Lie algebra of that is the same as the original, and here is the same. This obviously factors through neighborhoods of G0. So it can be applied also to local higher groupoids. And as I was saying, it's not much effort once you know everything, how to promote this instead of functions to forms. And what appears here on the right side is, so you have forms on G, and there is a Van Est map into the Weil algebra of AG, the Lie algebra of G. So the Weil algebra, I won't discuss this further, but once you have a higher Lie algebra, there is a way of defining the Weil algebra of it that generalizes the famous case of a Lie algebra going to the Weil algebra. And so here we get let's say, a lift of this Van Est map to forms. But the point is essentially the same. The procedure is the same. Okay, so now I want to discuss briefly the proof of this. In a sense, this is the main theorem because it tells you what differentiation is, and it characterizes it in terms of purely simplicial operations and so on. So how do we prove this? Thinking of the examples that I worked out now, the idea is that one should take functions on this G, do Taylor expansions, and then be very careful about which things are killed in the quotient. So to do this with care, so the first thing, as I already noticed, is the quotient, whatever it is a DGA, because J was a DG ideal. So that's clear. It will have a differential, and it will have a product. And also in degree 0, it's just functions by definition. So the definition of the higher algebroid, we just need to prove that it's commutative and that it admits this frame, so that it's freely generated. So in a sense, what we need to prove is regularity, that it's graded, commutative, and free, that there are no more relations and weird things. Okay, we already observed that the quotient localizes around G0, so we can just take this frame coming from theorem 1 and use the coordinates parameterized by these alphas that I already mentioned. We can even further, it's easy to see that the proof can be reduced to the case in which G0 is a coordinate neighborhood, for example, if you wanted to, or more interestingly, a neighborhood small enough such that all these bundles EK trivialize just by continuity. Okay, but even then there is lots of work to be done. First of all, these surjective maps that are here called beta, they can be parameterized combinatorially like this. For example, this is one such map. It goes from 4, 0, 1, 2, 3, 4 into 0, 1, 2. It has to be non-decreasing and it has to be surjective. So the information of what the map is captured by these two elements. Which one is the first that goes to 1, so that when you jump from 0 to 1, and which one is the first to go to 2? This is this I here. It's a collection of, in this case, the collection is just these two numbers, 2 and 3. Okay, so this is a way to parameterize such maps that appear in this Doltcan description. Now, okay, once you have such a collection, for example, I give you the numbers 1, 3, and 7, right? So this will be an I. It corresponds to one of these betas, and I can consider the corresponding coordinate and plug it into a polynomial. That is this one. So once I have a collection, I1, I2, IM of these indices that I'm calling here Q, and I have a multilinear map, I can just plug in the coordinates into the multilinear map and I obtain a polynomial. Okay, and the point of it is that the order of vanishing, when I look at this polynomial as a function, the order of vanishing is pretty much under control on each, even on each phase, on each degeneracy locus, S1, S2, and so on, because of these coordinates are very special. We have under control what is the order of vanishing of them. So these monomials will be the model, what remains after quotient. Okay, so we have what parameterizes these monomials is these two things. First, this collection of indices, and second is this map mu, this multilinear map. If you think of what happened in the examples of this multilinear map that doesn't have to be graded skew or anything, only the graded skew symmetric part will survive the quotient. That's the point. And that's how we will get the Chevalier-Eilenberg algebra. Okay, good. So this is the first result, that it's more or less just Taylor expansion. When you take Taylor expansion, only these monomials survive, but with the caveat that it has to, the collection I1 of indices that appear, I2 and so on. This is P, a collection. It has to be a covering. So if I get together all the numbers that appear here, they have to cover all of it, and there are no repetitions. So it's really a partition of this subset of numbers 1 to n into a partition of subsets. Because if there was repetition, it would mean that there is higher order of vanishing in this overlap, and then it dies in the quotient. Okay, so when you get into all this, this becomes more obvious. But okay, so these partitions parameterize the monomials that survive the quotient. So out of all smooth functions, we end up with just some certain polynomials. And the key lemma is this one, because it allows you to understand what are the new relations that one divides by. Here we were just dividing by J0, but we also have to divide by this delta of J0. So what is new in this delta? And essentially is this, that it's parameterized by coverings with one repetition. For example, you could have 1, 2. This is one index set, and the other one is 2, 3. So it covers everything, 1, 2, 3. But there is one repetition here in 2. And the idea is that such a collection Q is 2 set of indices with one repetition. It comes from 2 partitions with no repetition through the elementary sigma, the elementary surjection that repeats the number 2. Okay, so in a sense, very combinatorially, we know what we have to divide by. So what is going on here is that, anyway, you could have a partition that is 1, 2, 3, and 3, 4. So this is one possibility. This would be P1, for example. So this 2 that was repeated, now it's separated into 2 and 3. But you could also have 1, 3, and 2, 4, right? And this is the P2. And so in terms of these monomials, it tells you that when you exchange in the monomial the number 2 by the number 3, there is a minus sign. That's the new relation. Okay? This is pretty nice. Okay, this is the fundamental lemma to understand the quotient. Once you have this, you work a bit and you see that when you, for example, the cup product modulo J is graded commutative with the very precise Kosul sign that it's here. That the cup product goes to the wedge product in the free symmetric algebra, and that there are no extra relations. So it's some sort of miracle that I was mentioning, that thinking of these Taylor expansions, we unearthed graded commutativity in a refined way. So what I want to say is that there are many monomials, and you have to kill a lot of them. It's not just imposing this Kosul sign rule. There are many more relations that kill many things that you don't want and leave you with the graded symmetric algebra, graded symmetric algebra. Anyway, so this happens, and that's the theorem. And with this, you get for free, or you get structurally the Lie algebroid, the higher algebroid. If you want to extract higher bracket, everything you want to do is already there. So now, just to finish, this will be shorter. I will speak about the Van Est isomorphism theorem. So the idea in this theorem, the proof of the theorem will follow very closely a method that, well, I learned at least in a paper of Eckhart and David, with a double complex in the middle of the two things that you want to compare. So the theorem, now I'm making precise what is the topological condition. When you look at this D0 map that we already saw that it plays a fundamental role, the fibers of it have to have a certain connectedness with this number. Oh, I forgot to say. Here again, K have to be less or equal than N. Otherwise, yeah, you get an empty condition. Anyway, so the fibers of this map have to be less and less connected, but still connected. I mentioned the fact that when G is the nerve of a Lie groupoid or a Lie group, the fibers of this map, they all coincide with the fibers of the source map or the group itself. So we reproduce, we obtain again the same hypothesis that there is in the classical theorem of Van Est.
Can I ask
So,
if,
yes.
if you assume, maybe for simplicity, that G0 is a point, and then you take the geometric realization, does it imply that that thing has to be n connected?
That's a good question. I don't know. But no, well, it could be that yes, but my intuition says not, for the following fact. The geometric realization only sees the simplicial structure. So here there are two structures. And what is confusing is that simplicial, purely simplicial, like a simplicial set, can also, with this construction that you mentioned, be thought of as defining a space too. But here there are two spaces. One is the fact that GK, let's say, for K fixed, is a manifold, so it has the manifolds. And when you let K run, there is the simplicial structure that you can turn into a space. And this condition is on the first thing that I mentioned. So this the manifold structure. Does that make sense to you?
Yeah, I thought that that would be sort of taken into account because of that shifting as the K goes.
No. This is, for example, in a simple case, if you only care about H1, you just need the fibers of the source map, let's say, or the target map to be connected in the usual sense. It wouldn't have to do with the spatial realization.
But that spatial realization will be connected in that case, I think. Because
Yeah,
you're just,
maybe you're seeing something that I don't see, but a priori it makes reference to a different thing. Yeah, it could be that it's transformed into something, but I would imagine that the topological properties, I mean, yeah, maybe there is something that you might need to work a bit, and yes, I don't know. We can think more later. But yes, the idea here is that it makes reference to the manifold structures that are in these spaces. And so one comment that I can do about this is that this hypothesis, I mean, these fibers can be very large in a sense, but it can be transformed to show that it's equivalent to another hypothesis directly expressed in terms of the Horn filling maps, or the Horn projection map. So from, let's say, from GK now into the Horn K0. And these fibers are smaller. I just mentioned this one because it's easier to connect to the proof. And another comment is that just as in the case of groupoids, there is an analogous statement for forms where you fix, if you want, the degree of the forms. So you take whatever 3 forms and you get exactly the same thing, but now with the Veil algebra in degree, one of the 2 degrees equal to 3. Okay, so this will be the last slide. I will just explain what is the strategy of the proof. So a key object that is being used is something called double décalage, that in the universe of simplicial things, apparently is very well known. It's used in the proofs of fundamental things. The idea is that when you have a P simplex and a Q simplex, you can produce a new one with a certain procedure. And then you look at homomorphisms of simplices into G. So now, what can I say? It's like having 2 simplices like this, and in a sense, looking at different ways of connecting them, the vertices and so on. So this defines a purely here manifold is irrelevant. It's whenever you have a simplicial set, you have this double decalage. And the idea is that when you take cochains, you get a double complex. And because this double decalage, it's a bisimplicial object that is augmented in two different ways, then you get these two co-augmentations, where you get cochains on G vertically and also cochains on G horizontally. Of course, this construction comes with some contracting homotopies and things like this. So the cohomology of this G hat is completely trivial. And when you look at the map induced by this correspondence diagram, so you can play zigzag because the cohomology is trivial. So you can play zigzags and go from vertical to horizontal. The map you get, of course, is the identity. You didn't throw in any new information. Okay, this is almost what we want, but what we want to compare is cohomology of G and cohomology of the algebra. So what we will do is take this double complex and apply the differentiation functor vertically. So when I apply the differentiation functor vertically, I get another double complex, but now here on the lines is augmented by the Chevalier-Eilenberg. Okay, so you can think that this column has been differentiated to the Chevalier-Eilenberg, and then each one of the columns is differentiated into something that contains at the same time both information of G and of the algebra. They are mixed in, okay? So this is the main object for the proof, this double complex D. And again, what we want to do is prove that in cohomology, there are enough zeros here to play the zigzag game and define a map like this that will be an isomorphism in certain cohomology groups. So here is a remark that in the case of the nerve of a groupoid, when you do the whole thing and you differentiate vertically, you can check that what you obtain is foliated forms along this projection, along the fibers of this map that goes from E, the total space, into B. Okay, the fibers of this map, they are isomorphic to the source fibers of the groupoid or the target, you know. But so you have differential forms that are defined on this foliation, which are the fibers of this map, which is exactly what appears in this paper of Eckert and David, and also later Eckert and Maria Amelia Salazar. So this object that we define in general, it reproduces this double complex in this particular case. Good. So as I was saying, the strategy is to use zigzag. So essentially, if we want to compare cohomology in degree n on the groupoid and cohomology in degree n on the algebroid, we kind of need to play this game. So we want this triangular region below it to have zeros, okay, in cohomology. So the first observation is that when you look at the columns, of course, if you do this in a sophisticated way, there is a spectral sequence and whatnot, but things turn out to be more simple. When you look at the rows, which are kind of left intact, we didn't differentiate them. They are essentially the same information that of the double decalage. So there is a horizontal contracting homotopy for the rows. So the rows are still exact. So that's good. In a sense, that's you have to be a bit careful, but it's the same nonsense that happened before differentiation, because they were left intact. Now the columns are more delicate. So For the columns, we actually prove this proposition that I think has value on its own. It's about hypercovers. So hypercovers are certain maps between simplicial manifolds, I guess, with special property. It's when you think of higher stacks and so on, they are what you want to declare to be equivalences. So my collaborator Matthias noticed that what we needed for the columns can be abstracted more to isolate what we needed. It's about these hypercovers. So whenever you have a hypercover and has this property of being simple that I will mention in a second, then it induces an isomorphism in cohomology for the algebroid. So taking hypercover doesn't change the cohomology of the algebroids. Not of, if you think of the cohomology of G prime and G, this is very well known. But when you take the differentiation, then we prove this. This being M simple, it's a structural condition. Any hypercover can be decomposed into a tower of simple hypercovers with M equals 0, M equal 1, M equal 2. So this promotes, and it's important that the hypothesis need bigger than 0, because then what happens at M equals 0 survives, and that's where the topological condition enters. Okay, essentially what happens at M equals 0, when you look at this Postnikov tower of simple hypercovers, this one corresponds to the nerve of a submersion groupoid. And the submersion groupoid is exactly the submersion groupoid of this map that appeared in the hypothesis, but one for each column. That's why you need conditions on the fiber if you want to. Oh, by the way, by the classical Van Est, if you want, the submersion groupoid has algebroid these forms along the fibers, and if the fibers are whatever n connected, then the cohomology vanishes up to order n. So, and that's exactly what you need to produce the zeros that you want down here. And the topological condition was decreasing in K because of this triangle here, right? So when you are more to the right, like here, you need less of the map. And the map is this augmentation map going to this row here. Anyway, it's maybe too much detail, but I just wanted to stress that there is this very general statement about hypercovers that I think has value on its own. And then we apply it to the columns. And it's well known that the columns come from hypercover. So this double decalage defines hypercovers into a constant simplicial manifold and so on. Okay, so that's all I prepared. Sorry for going over time. I was thinking that I would go faster and then now there would be discussion, but I guess there are only few minutes to discuss, but okay.
Well, we have about 25 minutes left if people have
Okay,
energy,
okay.
but let's first thank Alejandro for the nice talk.